Hello, 1060. Here we are with our 5-3, the complex plane. So this first example says, find the complex conjugate of the given complex numbers. So here we go. We have a complex number. We know this is our real part. This is our imaginary part. And I just wanted to go over that really quickly. Your complex conjugate is just 9 minus 5i. All we have to do is change that middle sign. So for our second number there, it just becomes -2 plus I. So we can see that you just change your middle sign. Your complex plane is made up of a real axis and an imaginary axis. Note that this point Z is your distance x. So say it's over 5. And then up right here, maybe it's up 3i. So that's what 5 plus 3i would look. It would put you right here at that spot. So for example 2, we're going to convert complex numbers between rectangular form and polar form, and we're also going to graph. So just really quickly, if r is greater than or equal to 0 and theta is between 0 and 2 pi, the complex number z equals x plus yi may be written in polar form, and you're going to be asked to go from your complex number to a polar form quite a bit in this assignment. So just know that z equals x plus yi. This is our rectangular form, and then we just split it up into r cosine theta plus r sine theta times I, which we can simplify to this form here, and that's the form they use most in this section. Note that r is the magnitude or the modulus, and theta is called the argument of z, and that should answer some definition questions for you. Okay, so moving on, we're going to plot the complex numbers in the complex plane. This is our x right here, and this is our yi. So we're going to go over 4, positive 4, and then down 4 root 3, which is about 6.9. So I'll go over 4, down almost 7, and maybe I call that point A, so you can see where that is on my graph. For point B, we would go back 6 and then up 4, and that would be your point B. We're going to continue on with these problems and then write these rectangular numbers in polar form. To write them in polar form, we want it to look like r times cosine theta plus I sine theta. So to be able to do that, we have to find r first. To find r, we take the square root, remember this is x and y, of x squared plus y squared. And then to find theta, let me shorten that up a little. To find theta, we say tangent of theta is equal to y over x. So here we go. I'm going to take the information that I know to find r. I take the square root of x, which was 4 squared, plus -4 root 3 squared. And that, when I simplify that, gives me a value of 8. Then I'm going to find theta. Because I am looking for theta right here, I am going to take the inverse of tangent of my y value. My y value is -4 root 3 over 4, and this gives me an angle of -60 degrees. Now I want to think about this for just a second. -60 degrees. If I were to plot this point right here, I would go over 4 in the on the complex plane. I would go over 4 and down 4 root 3, which I just graphed just a second ago. That was point A in the slide before, and that was in quadrant 4. So now I'm thinking about a polar plane or a polar coordinate, or if I'm thinking about -60 degrees in quadrant 4, this actually correlates with 300 degrees, and that's what I'm going to use here. So to write this in this complex form that I just wrote up there previously, I take my r value, which was 8, times cosine of my angle, 300 degrees, plus I sine 300 degrees. And that is now in polar form. So I'm going to do the same thing for my second value, my negative 6 plus 4i. I'm going to find r by taking the square root of negative 6 squared plus 4 squared. And that will give me a value of the square root of 52, and then that reduces to 2 root 13, or simplifies to 2 root 13. Then to find theta, I'm going to take the inverse subtangent of 4 over negative 6, and this gives me an angle of negative 33 point, and I am going to do the nearest tenth, and these are going to be in degrees. I forgot to mention that. And then I want to think about this point. Remember this point when you graphed it on the previous slide, back 6 up 4, was in quadrant, I don't know, I wrote 4, quadrant 2, so I'm going to have to add 180 degrees to that negative 33.7 to get an angle in quadrant 2, and that's 146.3 degrees. And now I can go ahead and write my complex number in polar form. It will be 2 root 13, that's my r value, times cosine of my angle, 146.3, plus I sine 146.3. There you have it. Okay, on 6 and 7, he wants you to take your complex number that you have here and write it in rectangular form. To do that, we just have to calculate what cosine of 210 is. Cosine of 210 is negative root 3 over 2, and sine of 210 is negative 1/2. When I distribute the 7 through, I get negative 7 root 3 over 2, and I'll go ahead and write minus here, 7 over 2i. So same idea on this second value. Cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is negative 1. So when I multiply this, 6 times 0 is 0. So I just get a negative 6i. Okay, we have products and quotients of complex numbers. We get these rules. If r1 is cosine, or z1, it says z1 is r1 times cosine theta 1 plus I sine theta 1, and z2 is r2 times cosine theta 2 plus I sine theta 2. Be two complex numbers, then if we want to multiply or take a product, z1 times z2, we follow this formula, r1 times r2 times cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. If we want to take a quotient, we're going to divide those, and I take r1 divided by r2 times cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So all we're going to do in the next problems is apply these rules. So here we go. We're going to find the product first. So I'm going to take this r. Remember that this is r1. Here's my r2. And I'm going to go ahead and multiply those. 7 times 7. And I guess I could just write 49, but I'll go ahead and simplify in a minute. And then I take cosine of theta, oh, that looks like a Q, sorry, theta 1, here's theta 2. I'm going to take theta 1, which is pi over 9 plus pi over 12, plus I sine pi over 9 plus pi over 12. And then all I'm going to do is simplify that. 7 times 7 is 49. Cosine of pi over 9 plus pi over 12 will simplify and combine or add to give you 7 pi over 36 plus I sine 7 pi over 36. Then it also, oh, I lost a parenthesis there. It also would like you to take the quotient, C over W. So to do that, you take your 7 over 7, and then instead of adding those angles, we subtract them. and then all I'm going to do is simplify those. 7 over 7 is just 1. And pi over 9 minus pi over 12 gives you pi over 36. There you have it. So 9 is asking you to do the same thing, but it says we need to put it in polar form right now. If you recognize this is in rectangular, so we got to find r and theta for both of these. So maybe I call this r1 theta 1 for z, and then for w find r2 and theta 2. So to find r, we're going to take the square root of 7 squared plus a negative 7 squared. That gives you 7 root 2. For theta, we take the inverse of tangent of y, negative 7 over 7. And this will be in degrees. So when I take that inverse of tangent, negative 7 over 7, or just negative 1, I get negative 45. But remember, if I were to graph that point over 7, down 7, that would put me in quadrant 4. So really, I need to use the angle in quadrant 4 that correlates or corresponds with the negative 45, which is 315. All right, so let's do for W, let's find our R values. So to find our R values here, we take the square root of 3 squared plus 1 squared, which just gives us 2, and then we'll take the inverse of tangent of 1 over root 3, and that gives you 30 degrees. So now I can finally find z times w. Z times w, I take my r1, so 7 root 2, times my r2, which is 2, and then I take cosine, I take my angles and add them, so I get 315 plus 30 plus I sine of 315 plus 30, and then I'll just simplify this. 7 times 2 is 14, root 2, cosine of, I guess I don't need that parenthesis there, but it's fine, 345 plus I sine of 345. For, let's go ahead and now take z over w. Then I'm going to take my 7 root 2 over 2, and then take cosine of 315. Here we subtract our angles. And then I'll go ahead and simplify this. The 7 root 2 over 2 doesn't simplify. And then I have cosine of 285 plus I sine of 285. Okay, I'm not going to say his name correctly, but I'm going to try. De Moivre's theorem. It says if z equals r times cosine theta plus I sine theta is a complex number, then z to the nth power is equal to r to the nth times cosine of n theta plus I sine n theta, where n has to be greater than or equal to 1. So, on number 10, it is written in the form, our polar form right here. So we can go ahead and rewrite this to be an a plus. It wants us to take the expression and write it in standard form, a plus bi. So what I'm going to do is I'm going to rewrite this expression as 2. You can see 2 is my r. If you look right here, this is that form. And it's asking us to take it to the nth power, which is to the 4th power. So I'm just going to rewrite this piece. So I'll rewrite it as 2 to the 4th times cosine of 7 pi. Oh, I guess I could put n first. It doesn't matter, it's multiplication. My n is 4 times 7 pi over 6 plus I sine of 4 times 7 pi over 6. And then I'll just go ahead and simplify that. 2 to the 4th is 16. Cosine of 4 times 7 pi over 6 reduces to 14 pi over 3. And then I'll go ahead and take cosine of 14 pi over 3 is negative 1/2. And sine of 14 pi over 3 is root 3 over 2. And then I'll distribute that 16 through. 16 times a negative 1/2 is negative 8. And then I get plus, I'll go ahead and write it as 8i, because 16 times root 3 over 2 reduces to 8 over root 3, but I've got the I there, so I'll go 8i root 3. Okay, 11 is asking us to do the same thing, we just are not in a polar form yet. So to get this in polar form, we have to find r first. So to find r, this is your x and your y, so I'm going to take the square root of root 6 squared plus negative 1 squared, and that will give me the square root of 7. To find my angle, I take the inverse of tangent of y, negative 1 over root 6, and this is going to give me an angle that is about negative 22.2 degrees. However, it is going to ask me right here, if I think about this negative root 6 plus I, this would be back root 6 and up 1, and so that tells me I should be in quadrant 2. So if it's in quadrant 2, then I'm going to add 180 to this angle. My angle, oh, I just calculated that wrong. Sorry about that. That is not in quadrant 2. Over root 6 down 1 was in quadrant 4. I started to write quadrant 4. I don't know what I was thinking. Anyway, so that negative 22.2 degrees, if I want to think of the angle that corresponds with negative 22.2, it's 337.8. And so here we go. I'll go ahead and just write my polar form right now. My polar form would be root 7 times cosine of 337.8 plus I sine of 337.8, and then it's going to ask you to take this to the fourth. So when I take it to the fourth, I take root 7 to the fourth, and then I multiply by cosine of 4 times 337.8, I think I just said that, plus I sine of 4 times, maybe I should use some parentheses there, 337.8. And then we'll go ahead and simplify that. The square root of 7 to the fourth becomes 49. And then when I multiply 4 times that 337.8, I get 1351.2 degrees. And then I'll go ahead and take cosine of 1351.2 degrees, multiply that by 49, and I get 1.02 minus, it does turn into a negative, the I sine 49 times the I sine 1351.2 degrees gives you negative 40, it's like 48.989, so it's actually going to round up to, or in this case round down because it's negative 49.0 I. And that is in the form of A plus BI. Okay, so finding complex roots. So now it's going to say let W equal R times cosine theta minus I sine theta be a complex number where n is greater than or equal to 2, be an integer. If W is not equal to 0, then there are n distinct complex nth roots of W given by the formula. So whenever their n roots are, you will have n distinct complex roots. So here's our formula. And then it's important to know that k will equal 0, 1, 2, and so forth until you're 1 less than n. So example 3 says every non-zero complex number will have exactly how many distinct cubed roots? Well, then we'll have 3. That's what this is saying, n distinct nth roots. So every non-zero complex number will have exactly how many distinct fourth roots? And we'll have 4. So this says find all the complex roots, leave your answers in polar form with the argument in degrees. So we are writing our angle in degrees. It says the complex cube, this is important, cube root. So because it's cube root, we're looking for 3 values. But before we can actually go find those values, we are in a rectangular form. We need to convert this to polar. To convert this to polar, we start by finding r. So we take 7 squared plus 7 root 3 squared. And this will give you 14. And then we'll take the inverse of tangent of, 7 root 3 over 7. And this is 60 degrees. We just want to make sure if we go over 7, up 7 root 3, this point does lie in quadrant 1 of your complex plane, so 60 degrees also would be in the right quadrant. So, because it's asking to find the cubed root, we're going to take the cubed root of r. So that's 14 times cosine of, and I'm just following that formula, my angle, which was 60 degrees over 3, plus 2 pi k over 3, and then this is the same for your sine. So we have 60 over 3 plus 2 pi k over 3. And then because we are finding this for 3 roots, because it said find the cubed roots, then we need to find when k is equal to 0, 1, and 2. So to find our z sub 0 term, the cubed root of 14 stays the same. We can't reduce that. You will find that some there, you can reduce some of those. 60 divided by 3 simplifies to 20. If I put 0 in there, 0 times 2 pi is 0, 0 divided by 3 is 0, then I'm just left with 20 plus 0, so it's 20 degrees. For your z sub 1, we'll take the cubed root of 14 times cosine. Now this k right here becomes a 1, and this was 20. So then I have 20 plus 2 pi. It does say it in degrees, so I should have written that as 360, and that would be a lot easier. That's all right. 360 over 3, or 360 times 1 is 360 divided by 3 is 120. So we get 120 plus 20 gives me 140. Okay, to find our third value for z, same idea. We'll go ahead and put or substitute 2 in for k. I'm going to, instead of writing 2 pi there, I'm going to use 360 because it does want it in degrees. So I will have 20 plus 360 times 2 divided by 3 gives me 240. 240 plus 20 gives me 260. There you have it. Okay, 13 and 14 I'm going to do a little differently because I think it follows your homework better. But it says find all the complex roots. You're really not finding them all. You're just, well, you are finding all of them, not the first 3. So to find all of them, we're going to keep it in a general form. It does say use degrees, so this time I will use degrees. We have a complex number here in rectangular form. We want to turn it into polar form, so we take r by taking the square root. We don't have a real part, so that would be 0 squared plus negative 64 squared, which just gives us 64. So then I'm going to go ahead and to find theta, we take the inverse of tangent of negative 64 over 0, and that only occurs at 270 degrees. Just thinking about my unit circle, when is my cosine value positive and it's 0, and when is my sine value negative? That would occur at 270. So then to find all the complex roots, so you're going to go z sub k. You're finding all of them, not the first or the second or the third term. You're finding all of the terms. So here we take because we're doing a fourth roots, we'll take the fourth root of 64 times cosine of 270 over 4. It is in degrees, so I'm going to write it in degrees. So plus 360k over 4. We write the same fractions for your sine. In the simplified form, the fourth root of 64 is 2 root 2. And then this will simplify your 270 divided by 4 gives us 90. That's the second piece of that. 270 divided by 4 is not 90, it's 67.5. And then you would write plus 90k plus I sine of your 67.5 plus 90k. And that would find all of your complex roots. Okay. Here is your last problem. Hopefully you've made it through all of these problems. It says find the four complex fourth roots of w equals 256 and plot them on the complex plane. Well, before we can plot them, we actually need to take this 256 and find r. So r is the square root of 256 squared plus 0 squared, which makes it really easy. So r is 256. And then to find theta, we'll take the inverse of 0 over 256, which is just 0. So we have an angle of 0 degrees. And it does say find the four complex fourth roots. So we're going to take the fourth root of 256 times cosine of 0 over 4. Oops, I don't know what I did there. I think I moved stuff. Okay, I think I fixed that. 0 over 4 plus 360 over 4k. And then we will go ahead and add our I sine 0 over 4 plus 360 over 4k. And then I'll go ahead and simplify this to, we need to find 4 of them, so I'll start with k equals 0. The fourth root, so call this z0. The fourth root of 256 is just 4 times cosine of, if k is 0, that doesn't exist. So that's just cosine of 0 plus I sine of 0. And then when you distribute this through, or simplify this, cosine of 0 is 1. I sine, or sine of 0 is 0. Wow, struggling there. 0, which then just gives you a 0.4. So on my real axis, I would be out 4, and I wouldn't go anywhere on my imaginary axis. So we're going to do the same process for our next value. Now our k value is 1. So when I substitute 1 in here, 360 divided by 4 times 1 is just 90. So I got cosine of 90 plus I sine of 90. And I can do the same process. You're going to see what happens here. This just becomes 4i dividing z2. So now I substitute 2 in for k here. And I'm left with 180 degrees. And this gives me negative 4. I didn't graph the other one, so the other one is 4i, so I'd go up 4 on my imaginary axis. This one's back 4 on my real axis. I'm sure you can guess what my third point is going to look like. So our angle, if I substitute 3 in for k here, multiply that by 360, divide by 4, I get 270. Oh no, I did it again. 270, and that gives me negative 4i, so I'm down 4i, and you'll see that I create a circle. Alright, I hope this helps you with your assignment. Good luck.